Hello everyone, my name is Ted, and I'm very excited to introduce our revision paper, Declarative Data Serving, the Future of Machine Learning Inference on the Edge. This work is done at the University of Chicago in collaboration with Intel. So let's get started with model serving systems. There are existing such systems like Clipper, TensorFlow Serving, and TwitServe that are cloud-based machine learning inference as a service. They provide RESTful APIs for the users to call. For example, the user can upload an image of a cat, and the model service gets back to the user saying, okay, there's 90% of chance the image contains a cat, and there's also 10% of chance the image actually contains a dog. This has become a core component of machine learning applications. At the same time, we also see the prevalence of smart home devices. It is projected that 2.7 billion smart home devices will be installed in the US by 2023, and they gather a large amount of sensitive data in all forms, including video, audio, network packets, etc. That is where the edge computing comes into play. With edge computing, we can have very low latency while preserving the privacy and being regulatory compliant. So my question here is, can we move those model serving systems from the cloud to the edge? Here's an example use case of model serving system on the edge. In a smart home setting, we have video and audio from several cameras and microphones, and we're interested in if there's a person in the room. This is very useful in senior care use cases. And here, video and audio data needs to be aggregated together in order to issue a prediction, saying there's a person in the room or not. We have one server running the model serving system on the edge. So if you look at the bottom right figure, we call it the prediction node, number 3, and the data, number 1, collected from video and audio, need to be combined together at the right place in the right time. The model serving system here is actually doing the easiest part, which is inference. But the data movement between devices in the edge network is an underestimated challenge and is not solved in this case at all. This is not a trivial problem because in order to get the necessary data to be in the right place in the right time, we need two things, routing and placement. So if you imagine in a streaming setting, data just keeps coming in, but the model can stay there for a while without updating or retraining. There might be an issue between whether we want to move data to find the corresponding model sitting in a Jetson, or we might want to move a model to match the data already flowing into a Jetson, where Jetson is an edge device with a GPU doing the model inference. So such decisions will depend on, first, the design of machine learning model, and second, the necessary data flows needed to transfer to support that model, and third, the available resources in the edge network. So basically, we need to trade off between accuracy, communication, and computation, and the trade-off is currently handled by users themselves because there's no architecture that supports data movement for model serving on the edge. So our motivation is the same way that database community has made sure people don't explicitly program iterators for database query processing. We want to make it similar for machine learning model inference on the edge. We want to make sure that people are not hand coding the data routing rules because that would be too brittle to networking changes. So we declaratively make sure all data get to the right place in the right time. Our solution to this problem is to configure data flows between edge nodes declaratively through high-level constraints. So if you look at the figure here, it is an overall architecture of our system, and there are 4 key components we will introduce in detail shortly. First, we have data input with the streaming data sources, workload description, and the user preferences. And we have a centralized cost-based optimizer to determine model placement and data routing for the execution engine to run. And 3, we have execution engine, which it will either issue a prediction on the edge or it will sync with the cloud to issue a final prediction on the cloud. We have the 4th cloud synchronization layer to update and retrain the model if necessary. So here in the data input layer, the user describes which node to collect data, how those nodes are connected, the trained models to serve, where to deliver those model predictions, and the preference between trade-offs, like if you prefer the accuracy over communication. And second, we have the optimizer, where the centralized cost-based optimizer parses all the information given by number one, and it also oversees the edge network as a scheduler. It determines where to best place models and how to route data through the edge network. It needs cost modeling of contention, latency, and accuracy on all the edge nodes, while also satisfying the locality constraints of every model inference task. So you can see that this is the key component of our system. It is also the most important part to achieve how we declaratively achieve the data serving. And then after we have the optimization result, the execution engine is a push-based producer consumer system where the producer is raw data streams and consumer is model inference tasks. It takes all the instructions given by the optimizer and just do the execution. Finally, we have cloud synchronization layer, where we synchronize data with cloud services for model retraining and updating. We also transfer data to the cloud if the edge resources are overloaded with the existing work. So this is a dynamic process. We make sure that we don't spend extra money and we spend money if we do need to. So currently we have built an initial prototype using Kafka as the message broker. We are working with Professor Nick Finster at the University of Chicago's IoT lab, building an edge cluster with all the specialized edge hardware we know. For example, we have NVIDIA Jetson with GPU equipped. We have Intel's VPU. We have Google's Edge TPU. And with those edge devices, we are able to do some machine learning model serving tasks that are usually done only on the cloud and on the edge, on the high-end GPUs. So once we build out this system, it will really change how model inference works. There will be new research questions, and here's just one example. We argue that people will need to rethink how communication is important in the edge network. For example, we have communication-efficient models developed by machine learning researchers. This figure below shows how machine learning model structure plays an intimate role in how much data are communicated to serve the prediction. So if you look at the figure on the left, we have a model that integrates the 3 data sources at the input layer, while on the right, we have another model that integrates data at a later layer. The model on the right is potentially more communication efficient than the model on the left. And we believe that it is possible to integrate such constraints into the model searching process. For example, we can only consider the neural network architectures with a certain communication cost. So balancing those constraints with accuracy will be an important future research challenge for the machine learning researchers. Another research question is efficiency robustness trade-off in multimodal models. If we have multiple resources of data aggregated together to issue a prediction, we can either ensemble the models with the majority vote, or we can also train a unified model with the multiple sources of data. The assembling approach may lose correlations across data sources, but it can serve predictions even after losing input data sources. On the other hand, if we only train one single unified model, it is able to pick up correlations between data sources, but it will not be accurate enough if one of the inputs is lost. There are also, of course, system research questions like optimizer, multi-tenancy, fault tolerance, and privacy, but I will not cover those items in detail. So I guess that's it. Thank you for your time, and feel free to ask me any questions or drop me a line at swjz@uchicago.edu.